with tangent lines and interpreting the meaning of a derivative in the context, and then also some work with approximation using what they call local linearity, which just is a fancy way of saying tangent line. So remember that a tangent line, if you have the point, and there may be, you're going to have the point that's a comma f of a, so two values, an x value and a y value, and you have the slope, and the slope in calculus we find as f prime of a. All of these are just values, right? So make sure that these are not equations, they're not expressions with x and y in them, they are actual numerical values. Both of these are numerical values. So don't get confused and start putting an expression for the slope in. But for the numerical values, then the equation of the tangent line is y equals f prime of a times x minus a plus f of a. If you don't know that equation by now, you should actually just sit there and write it 10 times and write it again until you know it by heart, because it's an equation that we will use for a long time in calculus. So interpreting the units in context, I'm going to start with this thing that I created a number of years ago, that it was the step diagram. And when we go up this way, we use differentiation. When we go down the steps, we're going to use integration. But at this point, when you think about these steps and we take the derivative, it's kind of like, generically speaking, if this is f, this would be f prime, and this would be f double prime. It could be that we call it g, and so just know that we could call it a lot of different things here. So units of measure. So just thinking in terms of units, maybe this is in inches. Then this one is inches per some time limit, let's say it's minutes. Then this would be in inches per minute squared, because each time we're going up by another factor of minutes. We could do it in terms of like water flow, and it might be that this is gallons, and then this is gallons maybe, and this time the unit of measure is maybe seconds, and this time is the gallons, and this would be seconds squared, because each time we go up by another unit of measure. It could be that we're talking about people in line at an amusement park, right? So we could have that this is people. So then this would be people maybe per hour. Then this one would be people per hour squared. It could be in weight, right? I mean, it could be, let's say we're dealing with something where maybe it's sand, and so this is in tons. Then this is maybe in tons per day. Then this one is in tons per day squared. So just know that that's the way the context and units are going to go. And you actually can move up or down the steps. So you got to kind of think, well, what step am I on and where am I going and what's its relation to what I have, and then kind of pay attention to units. Because in truth, in a different context, I could make this g prime, then this would be g double prime, and this would be g triple prime. So, I mean, it doesn't matter because you're just going up another derivative. There is actually a context of f triple prime, which is, but we won't get into it. As far as AP Calculus goes, this is as far as we're going to go. Now, remember what the average rate of change is. The average rate of change is the same thing as the slope. So if you have a table, that's just simply doing f of b minus f of a divided by b minus a. It's used with a table or a graph, usually. Local linearity. This is using a tangent line equation for an approximation. So that's what local linearity is talking about. It's using a tangent line equation for an approximation. So I got a couple of examples. So let's take something like this. If we were going to write the equation of this tangent line using a calculator and rounding it to 3 decimal places, round all the decimals to 3 decimal places, what we'd want is we would want y equals f prime of negative 0.5 times x minus negative 0.5 plus f of negative 0.5. Now, a couple things that you want on your calculator. It needs to be in radians. Okay, so I think we already converted them to radians. Remember, for the derivative, you use, let me grab my calculator, make sure I tell you exactly. You're going to type in menu, then you're going to go to number 4, and then you're going to go to number 1 and follow the directions for that. To evaluate this function, to evaluate the function, just plug it into that equation that's right up there. I'm not going to go through it, but then you're just going to write the equation. Round things to 3 decimal places. Okay, so let's take a look at this thing. The rate at which the temperature of an object is changing is in degrees Celsius per minute. So the rate can be modeled by this function. The temperature of the object at T equals 13 is 56 degrees. Okay, so the temperature is 56 degrees. Selected values of R of T are shown in the table above. Use the linear approximation when T equals 13 to come up with an estimate for the temperature at T equals 12.9. So we're kind of centered around this. Okay. Well, so let's think about what this is. That R of T is really what's referring to, that's really that idea of slope. Because that's what R of T is. Remember, it's a rate. A rate in degrees Celsius is R of T, so that's a slope. So if we were going to write the tangent line for this, we'd write y equals 2, which is the slope, x minus 13 plus 56. Now, if we wanted to then figure out what this is, really that x is not x necessarily. That x is really t. That y is not y really. That y is really the temperature. So we use this r of t because that's the rate of change. Remember, that's the rate of change. And then that point, you have that point right there. So your point is 13, 56, and your slope is 2. So then we just plug in 12.9 into that. So if we wanted to finish this, we would write temperature is equal to 2 times 12.9 minus 13 plus 56. Now, proper units on this. Remember, so if you think about what this is this is a temperature, right? That's a temperature. So the end result on this should be degrees Celsius. That's what the unit of measure has to be on that, because that equation is giving a temperature, so the unit of measure on that one would be degrees Celsius. Okay, here's example 3. The rate at which the amount of water in a tank is changing is in liters per minute and is modeled by this function. So again, this is a rate, and it is in liters per minute. Can be modeled by the function c of t, where t is measured in minutes. So this is in minutes. Selected values of c of t are shown in the table above. Use the data in the table to estimate 8.5, indicating your unit of measure. So c prime of 8.5. So that's c prime is the slope of c. Now, 8.5 is right in this area. 8.5. So that's the values I'm going to use. These are the values I'm going to use from this table. I'm going to use these values to come up with my answer. If I use those values, the y values would be 9 minus 2. So what I'm going to do is let me erase this for a second. Let me go through here and say, okay, c prime of 8.5, according to this table, is approximately equal to 9 minus 2 divided by 6 minus 11. So if I calculate this, this would be 7 over negative 5. Now, if you're wondering what the unit of measure is, maybe you already know. Maybe you already know what the unit of measure is. If c is in liters per minute, you hopefully know that c prime of 8.5 is negative 7/5, and you maybe already know it's in liters per minute squared. Another way of kind of coming up with that value is think about what the numerator on this thing is. The numerator on this is liters per minute, and the denominator is in minutes. Together, that's liters per minute squared. So think about back into your chemistry days when you were converting to moles. That's just a unit conversion kind of thing. That's just a looking at units. Liters per minute divided by minutes is liters per minute squared. Hopefully that makes sense. Good luck on the assignment. Let me know if you have any questions.